Example 2.6. The working substance is a monatomic neon gas. A. Draw an accurate energy bar diagram for the cycle that clearly shows appropriate height changes. Rank all the workings, heatings, and changes in internal energy. B. Determine the pressure, temperature, and volumes at the gas at points 1, 2, and 3, where P1 is the atmospheric pressure. Put your results in a table for easy reading. C. Determine the workings, heatings, and changes in internal energy for each path. D. As a check, the following must be true for your numerical values. The sum of internal energies around the cycle should be 0, and the net heat must be the negative of the net work. Do these agree with what you calculated? So here's what we know. We know we have a monatomic gas. So that tells us three things immediately. CV is 3/2 R. CP is 5/3 R, 5/2 R. And the ratio of CP to CV, gamma, is 5/3. Okay, so the first thing I need to do here is that I need to go in and I need to draw a bar diagram so that I have a good overall view of what is happening. So draw a bar diagram. And rank the heat, the works, and the changes in internal energies. So first thing I'm going to do here is that I have my cycle right here, and we should be carrying that around because we're going to need it. So let's start looking at this. So I'm going to start with path 1. So path 1 to 2. So when I look at that, that's clearly isochoric heating. And so what happens here is that I know that the work from 1 to 2 is 0 because the gas does not lose any kinetic energy when it collides with the piston head. But in order to increase pressure, that means that the heat that goes in now increases the internal energy of the gas, which should be positive. So now let's look at the path from 2 to 3. Well, this is an adiabatic cooling / expansion. Now, the fact that we say the word expansion means that the work must be negative. The kinetic energy of the gases decrease as they collide with the piston head. Definition of adiabatic is that there's no heat transfer, so therefore the work from 2 to 3 must be the same as the internal energy for 2 to 3, and that's got to be negative. And then finally, we have the last leg of the cycle, 3 to 1. Here we see that this is an isobaric cooling / compression. So when the piston head compresses, it's doing work on the gases and it increases their kinetic energy. So therefore the work must be positive. But we're going from a higher energy state to a lower energy state. So I would expect that the heat is going to be negative as well as the internal energy being negative. I have to take out heat to keep the pressure smaller when we have as the compression occurs. So now let's draw our energy bar diagram. So what I'm going to do here is that I'm just going to make some arbitrary height. So let's see here, 1, 2, 3, 4, 5. So I'm going to start right here and I'm going to say here is my internal energy where I got to start. So I'm gonna look at the whole cycle here. So when I look at the cycle, this is my initial energy at state 1. So now what happens? Look at what state 1 says. I have 0 work, right? I have 0 work from 1 to 2, but I add heat. So the heat increases the kinetic energy. So what I'm going to assume here is that I'm going to add 3 squares of heat. So now I see that I'm now increasing my internal energy. Now let's look at this thing. As I increase my internal energy, I have to increase this guy by 3 squares. So it's right here, so I got to go up 3 squares. And this is my internal energy right here. So this is internal energy 2. And so when I look at the change in internal energy, you can see that from here to there is my change in internal energy between 1 and 2. And note that this guy is positive. So that's a positive increase. Now I get to the path between 2 and 3. Now between the path between 2 and 3, what's going to happen here is that I immediately see that there is no work. Excuse me, there's no heat. For an adiabatic process, there's no heat. Now, the thing that I want you to pay attention here is that look at the area under the curve between 2 and 3 and compare it to the area between 3 and 1. So my bar size has to be bigger between 2 and 3 than 3 and 1. So that means here, I'm going to say that this is 2 squares to represent the work between 2 and 3. Now note that has to be negative because it's an expansion. So that means there's a decrease in internal energy. So when I look at this thing, if this is 2 squares, then my internal energy has to drop to right here. Right? So I now have a decrease in internal energy, and this is my internal energy at state 3. Look at the height change. So the height change then tells me that I'm going to have a negative change in internal energy because it's a decrease. So now what happens here is that I'm now going to go in, and I know for a fact that if I'm going to get back to state 1, my final internal energy has to be exactly the same as I initially started. So I know it has to be this way. So now look what happens. Between 3 and 1, I have positive work, and I have to eject heat. Now here's where the point that I made earlier. Look at the work from 2 to 3 versus 3 to 1. The size of the bar has to be smaller. So I'm going to come in here, and I'm going to draw my bar right here for the work between 3 and 1. Note that that is positive. So now that sets my heat. Because when I look at the change in internal energy, note that this change is negative from 3 to 1. So that means I have to set my heat so that it does what? It kills off the work right here. And then once it kills off the work, I have to remove enough heat that I get the right height change. So what you're seeing here is that now this represents my heat from 3 to 1. So now we can just rank the things here. So now let's rank the heatings, workings, and internal energies. So the first thing that I note here is that note that Q12 is positive, Q23 is 0, but Q31 is negative. 0 is greater than a negative number, so this has to be Q31. Now let's look at the workings. If I look at the work, I only have one positive work, which is the work from 3 to 1. And then, again, 0 is bigger than a negative number, so therefore the work 2, 3 is the smallest. And then finally, I look at the internal energy. You could see here is that I only have one positive change in internal energy, which is 1, 2. Now look at the energy between 3, 1 versus 2, 3. 3, 1 has a less negative number, so then that comes in as second. And then the last, because it's a bigger negative number, comes in right here. So now we have our rankings. And I think what's going to be really important at the very end, we should check to see if our rankings make sense when we make numerical computations. So here we go. So now what I want to do here is that I want to calculate all the pressures, volumes, and temperatures. So here we go. So here we want to calculate all pressures, volumes, temperatures. So let's go do that. So note, we are not given a mole number. So because we're not given a mole number, this strongly suggests that you should be using the ideal gas law conditions, not the ideal gas law equation. And we'll look here in a moment to see if it makes sense here. So the first thing I need to do is that I need to convert all the data into proper units. So what I'm going to do here is that I have this guy here. And the one thing that you want to remember here is that we have values that are already given. So let's go look at what we have. So the first thing that we see is that we know that pressure P1 is atmospheric pressure. So I'm going to convert that to pascals immediately. Then look at the temperature T1. Temperature T1, that's 133 degrees, but we immediately convert that into Kelvin, which then reads 406 K. And then finally, you could see that we have V1. V1 is 10 to the 3. And then I'm going to convert centimeters into meters. So maybe I should put centimeters cubed right here. And then if I convert that, this is going to be 1 meter over 10 to the 2 centimeters. And then I have to cube it, and that gives me 10 to the minus 3 meters cubed. So note, I know everything about state 1. Like, and we should really, look at this thing here to make sure that we're actually, let me paste in. So I already set up a table. So just to do this, efficiently. So let's look at what we need to calculate. So the first thing that I see here is that I have atmospheric pressure. I have, at state 2, I have pressure 5.05, which is 5 atmospheres. And if you look at state 3, we know all of the pressures in here. So when I look at this thing, the temperature, I only have one temperature at state 1. And then the volume of state 1 and 2 is the same. So this is going to be a value of 1. So you could see here that there are 3 values that I don't know. So you could see here is that our goal is to calculate T2, T3, and the volume at 3. That's what we got to do. So let's start looking at this thing. So you know what? I'm going to copy this so that I have this with me. And I could keep moving this thing down. So I want to focus on state 1. And what I'm saying here is that note all 3 state variables are known here, right? I got the pressure, the temperature, the volume. So this allows one to calculate the mole number. But my question is, do we need to? And I'm saying, in general, no. Use the ideal gas law conditions to compute T2, T3, V3. My job here is to really show you that that there's other ways to calculate these quantities besides the ideal gas law. And many of the times, the ideal gas law conditions are much, much easier. So let's look at this thing here. So the first thing that I'm going to do here is that look at the process between 1 and 2. That's isochoric heating. So the volume is constant. So because I know the pressures and 1 volume, I have 3 out of the 4 variables. This is what I mean here. So let's look at the isochoric process 1 to 2. So when I look at the isochoric process, what that really tells me is that I'm getting what? I'm getting isochoric heating. And so what that allows me here is it says that the volume, which is a constant, is proportional to the temperature and pressure ratio. So if I put this down, I find that I get T1, P1. Now note, if I look at the temperature and the pressure, the fact that the pressure is higher, it automatically implies that the temperature must be higher. So now what I'm going to do here is I'm going to solve for T2, since that's one of the quantities that I don't know. So then if I do this, then I'm going to get the ratio of pressures times the temperature 1. So then if I start putting in my values, now note there's 10 to the 5, but there's a 10 to the 5 in the numerator and denominator, so they cancel out. So I'm only going after the cofactor. So this will be 5.05, 1.01 times the temperature, which is 406 K. So when I compute that, I get 2030 Kelvin, and I now have the pressure or the temperature at state 2. Now look at that. If I did the ideal gas law approach, I would have to do a calculation to get the mole number, and then I would have to punch in a bunch of numbers to actually get the temperature 2 at that state. This was much faster. and cleaner. Now, let's look at that. So if I now come in and I put in my values here, look at this. I now have this value for the temperature. So now let's look at the path between 2 and 3, which is an adiabatic expansion, cooling expansion. So let's look at that. So now I have an adiabatic process as I go from 2 to 3. Now remember, we wanted to calculate temperature 2, temperature 3, and volume 3. So if I look at the adiabatic, what that's really telling me is that I'm going after the volume 3. So here I go. So I know that I have what I have here is that I have adiabatic cooling, which means I should see the temperature drop, and I have an expansion, but that tells me that this pressure times the volume has to be a constant. So now that I have that, let's go calculate this thing here. Okay, so now with this adiabatic expansion, it's connecting 2 to 3. So let's focus on that. So now we're going to use this to calculate volume 3. So then the condition says P2 V2 gamma must be P3 V3 gamma. And so when I'm looking at this thing, my goal here is that I want to do what? I want to solve for V3. So if I solve for V3, let's see what happens. So if I isolate V3, that means I got to bring over P3. So note that I have P2, P3. But let's be careful now. In order to isolate V3, I have to take the inverse of gamma. So that means that the pressures now have the inverse of gamma. And if I take the inverse of gamma on the volume, you're going to see here is that now I'd have the volume with no gamma factor. Now, even though I didn't say this, gamma in this case is 5/3 because that's the ratio of CP/CV. So when I plug in my numbers, I'm going to have 5.05, 1.01, and this is 1 over gamma, but 1 over gamma is the same as 3/5. And then my volume, which is 1 times 10 to the negative 3 meters cubed, you can see that if I compute that, I get 2.63 times 10 to the minus 3 meters cubed. So now I have my volume 3. So now that I've computed the volume, I'm only left with temperature 3 that I have to calculate. So when I look at temperature 3, I could use the adiabatic process to calculate that temperature 3. I'd have to convert the pressure into a temperature. Or the other thing that we could do here is that we can use the process between 3 and 1, which is an isobaric cooling process. So I think we should use the isobaric just because it's a different process and we can sort of look at that. So now I have an isobaric process between 3 and 1. So in this case, this is isobaric cooling / compression. And this tells us that the pressure has to be a constant. And so then the ratio of temperature to volume should also be a constant. Note they're not equal to the same constant. But the fact is that I could now look and look at this thing here. So now what I'm going to do here is that I'm going to use this to calculate T3. So if I do that, what do I actually have? Well, this tells me that T3 over B3 and T1 over V1, this will now allow me to solve for T3. So then solving for T3, I then have the ratio of volumes to temperature 1. So now if I start to bring in my values, look at that. I know what the volume is, and I know what temperature 1 is. So now I could then put those all to use here. So this will then be what? 2.63. Now note times 10 to the negative 3 divided by 1 times 10 to the negative 3 times the temperature of 406 K. I now get a temperature of 1068 Kelvin for T3. So now I have my values. So in summary, here's what we have. So if I come in, I believe I still have my table. If it ever comes up. There it is. So now I could now put in my values here. And if I look at all the values, you'll note that we initially put in 20, 30, and then we just computed 1068. And then our volume here was 2.63. Once again, did not use the ideal gas law equation. We use the conditions to compute all of these guys here. Okay, so now we need to go on to part C, where now we want to compute all of the heatings and workings and stuff like that. So here we go. So now C, we want to calculate all the heatings, workings, and changes in internal energy. So once again, the first thing I got to do here is that I have to keep my system right here. Right, so I'm going to use this to actually tell me about what do I have. So what I'm going to do here is that I already prepared a table to try to be fast here, and you could see that this is a pre-prepared table, so you don't see me write this stuff down. So I want to move this over if it allows me. Looks like my computer's slowing down. Okay, so let's go look at this guy here. So the first thing that you see here is that because of these processes, we can immediately talk about what we know about immediately. So we know from right from the get-go here is that we have what? We know that process 1 to 2 you can see it's an isochoric, so this immediately tells me that the work is 0. So when I look at this, this tells me that the heat between 1 and 2 and the internal energy between 1 and 2, well, that's the same. So that's one calculation to calculate all of these. And so what you're seeing here is that the process from 2 to 3 is adiabatic, so I know that the heat is 0. So what I need to calculate here is that I now know that the work between 2 and 3 is also the internal energy between 2 and 3. And then when I get to state 3 to 1, I'm going to need all 3 quantities. So this guy tells me that I'm going to need the work from 3 to 1. I'm going to need the, let's say, the heat from 3 to 1, and I'm going to let the internal energy between 3 and 1. But note that I would not individually calculate both of these. So do not calculate both, but use the first law. So if I calculate the internal energy, then I use the first law to calculate the heating here. So now that I have that, here's what I want to do here. I want to go in and I want to now start calculating these values. So I'm going to start with the first cycle. So I have my isobaric process from 1 to 2. So what do I know about that isobaric process? Well, we already know here that the work between 1 and 2 is 0. And so I'm going to use the internal energy between 1 and 2 to calculate the heat between 1 and 2, since they're the same. So let's calculate the internal energy between 1 and 2. Now note, I could calculate the heat just as easily. Okay? I could calculate the heat just as easily at constant volume heating. But it turns out that they have to be the same. So in this case, here's I go. So now the internal energy between 1 and 2 has to be NCV times the temperature 1 to 2. Now, if I put in my CV value, I have NR delta T 1, 2. Now, if I write this out with that ideal gas trick that I talked about, this is the same as what? 3/2. Now look what you get. You get NR T2 minus NR T1, but now I use the ideal gas here. So now use ideal gas law equation. And when you do that, I can rewrite this so that now this becomes 3/2 of P2 V2 P1 V1. But since the volume, this is an isochoric. Oh, look at that. I called it isobaric. That's wrong. It should be isochoric. Bad language. So now, note that the volume is fixed. So this should really be 3/2 times the difference in pressure with a fixed volume. So now, what do? I'm just going to use these values off my table, right? I know the pressures and I know the volumes. So I'm going to put those right in right here. So now if I come in and I start to put these numerically, look what I'm going to get. I'm going to get 3/2, the pressure difference, which will be 5.05 minus 1.01. Note, I did not put 10 to the 5 in there, but look where I'm going to put it. Here's my 10 to the 5 for the pascals. Now the volume is 10 to the minus 3. So what you're going to see here is that this little guy keeps popping up. So 10 to the 5 times 10 to the minus 3 is always going to be 10 to the 2 times 100. So that means all of our heatings, workings, and internal energy are going to be the order of 100. So then if I compute this, I get a value of positive 606 joules. And that's going to be my internal energy between 1 and 2, which will then be the heating between 1 and 2. So now I've calculated these guys here. Okay. So now I know everything about that isochoric process. Now let's go to the next one. So now I'm going to look at my adiabatic. And that's between 2 and 3. So I want to calculate everything about this process here. So when I look at this process, what do I actually see here? Well, I know that the heat between two of them is clearly 0. So then that tells me that I should not try to calculate the work because you got that curve. That requires an integral. The easier way to do this is to calculate the internal energy change to get the work. So let's go do that. So if I do that, here's what happens now. So for the adiabatic process, I'm going to calculate the internal energy between 2 and 3. So here we go. The internal energy between 2 and 3 is identical to the previous situation. So now I'm going to have NCV, the temperature change between 2 and 3. But remember, we don't want the temperature change. So if I do this, I'm going to get 3/2 NR, the change in temperature between 2 and 3. And if I use the ideal gas law trick that I talked about, this is 3/2 NR. Oops, nope. This is going, I can convert that to the pressures and volumes. So this will be pressure 3, volume 3, pressure 2, volume 2. So now I plug in those values. So again, where am I getting these values? From this table. Look at 2 and 3. I got 5 and 1 atmospheres, and then I have 1 and 2.6 times 10 to the negative 3. So now look what happens. So I'm going to plug in my values. So then I'm going to get 3/2. So now I look at my pressures. So my pressure at 3 is now atmospheric pressure. So it's 1.01, but the volume has increased to 2.63 minus 5 atmospheres times a volume of 1. Now look at that 10 to the 5 and look at that 10 to the 3. This guy turns out to be 10 to the 2. And this will be in joules. So when I compute that, I get minus 356 joules, which is now my internal energy between 2 and 3 and my work between 2 and 3. Note no integrals here. So now if I look at this, I now have almost all my values. So now I just need the values for cycle 3-1. So now here I go. So the next one I need to do here is that I need to do the isobaric, right? I need the isobaric process between 3 and 1. So what we talked about with the isobaric process is that I'm going to calculate the area of 1. Then I'm going to calculate the internal energy like this and use the first law to get the heating of 3-1, which will then be the internal energy of 3-1 minus the work 3-1. That's the most efficient. So the first thing I'm going to do here is that I want to calculate the work between 3 and 1. So you know that before I do that, I'm going to bring that table over here. And I'm going to start to fill in my values. But I definitely want to, carry this PVD diagram so that it's easy to make sense of what's going on. So the first thing that I want to do here is that note that I need this area right here. And that's just an area of a rectangle. right? That's the area of a rectangle. So let's compute that. So then, because it's a compression, we know that this work between 3 and 1 has to be positive. And then I need the area of that rectangle. So then this guy's going to be what? It's going to be P1, 0. That's the height. Then the width is V3 minus V1. So now I'm going to put everything in. So I'm going to get 1.01. Now note it's the difference in the volumes, which will be 2.63 minus 1. But note I get 10 to the 5 times 10 to the 3, which then gives me 10 to the 2 joules. So when I compute this, I get a value of positive 165 joules for the work between 3 and 1. So now that I have the table here, we should probably start putting in the values. So look at for process 1, 2, I have 606. So we already said that this was 0. Let me not do that. I want that in black. So then this guy is going to be positive 606, positive 606. Then I look at the work and the internal energy. So then this guy's going to be negative 356. And then this will be minus 356. And we just calculated our work, which is positive 165. So I just need 2 more quantities to calculate. So then what I said here is that I would calculate the internal energy first. So I will now want to calculate the internal energy between 3 and 1. So we know that guy has to be negative. So here I go. I'm going to use the exact same process. So if I use the exact same process, then I'm going to move a little bit faster here. So this is going to be N CV delta T 3, 1. So note I'm going to convert the the temperatures into pressures and volumes. So then this should be what? It should be 3/2. So then it should be P1 V1 minus P3 V3. But because this is isobaric, the pressure P1 and 3/1 are the same. So this should be 3/2 P1 times the difference 1 minus V3. And look at that. The quantity V1 minus V3 is negative. So now let's punch in the numbers. So if I punch in the numbers, this is going to be what? 3/2. Then the pressure here is going to be 1.01 times 1 minus 2.63. And then remember, I get that 10 to the 2 value, joules. And so when I get this value, I get minus 247 joules for the change in internal energy 3/1. So now that I have my internal energy, I can go compute the heat. So from the first law, so I'm going to calculate heating 3/1 from first law. So if I look at that, then the first law says that the heat between 3/1 is going to be the change in internal energy minus the work. So if I punch in my values, note that I'm going to get minus 247 plus minus, oh, nope, that should be a minus, not a plus, minus 165. So if I compute that, I get minus 412 joules, which will then give me the heat between 3 and 1. So you could see here is that the heat was ejected. So now if I punch in the rest of my values here, this is going to be minus 412, and then this will be minus 247. So what I want to do here is that in summary, let's check these values from our bar diagram. Because we rank these guys, right? Because we rank these guys, we want to check them to make sure that that's what we're seeing in this table. So look what I'm going to do. I'm going to go all the way back up, and this is what I want right here. I want these rankings. Okay, I'm going to copy this, and I'm going to bring them all the way back down. So here they are right here. So here's was our initial rankings. So now, is this true? So if I look at this guy, what are the heatings here? So if I look at the heatings, I get what? I get plus 606 greater than 0 greater than minus 412 joules. Hey, that matches up pretty well. Now let's look at the workings. It says the positive work was going to be 3,1. So look at this. So then the positive work is positive 165 joules, 0, and then we have what? A negative minus 356 joules. That's matching up exactly what we were looking at as far as the size here. And then finally, the internal energy. We see that the internal energy was going to be what? It's going to be, the first one was 606. So this is 606 joules, and that had to be greater than 23. And look at that. There's a smaller negative number, as we talked about, and then I get a bigger negative number in minus 356 joules. So that is matching up quite well here, really well. So that bar diagram really does give you intuition as to what is happening here. So now what I'm going to do is that I'm going to check all of these things. So I'm going to go to D, and I want to do a check on all the results to see if they make sense. So what do I mean by that? Well, we know that if we have a cyclic process, you come back to the initial point, and then the state should be exactly the same. So therefore, my change in internal energy must be 0. But according to the first law, that says that the net work and the net heat added should also equal to 0. So then that means that the net heat must be the negative of the net work. Okay, so let's go check it. So there's two conditions. There's the cycle of the internal energies has to be equal to 0. So are they 0? Okay, so what I'm going to do here is that I'm going to punch in my table right here so that I don't have to really, go back and forth. So let's go check this. So the first thing I'm going to check is that I'm going to check, is the cycle of the internal energy equal to 0? That's the question that we're asking here. So in this case, that means that the internal energy between 1 and 2 plus 2 and 3 plus 3, 1, well, is that 0? So what you're seeing here is that I'm just adding these 3 values, and I'm going to punch them into the square down below. So if I apply this, this is really what? Positive 606 minus 356 minus 247, and that gives me 1 joule. So the value that I get is 1 joule. So is that 0? And I'm going to say, well, absolutely. And the reason why I even get 1 0 because this is due to rounding errors. So yeah, that perfectly matches up. So then the other thing here is that I need to calculate the net heat and the net works here. So now the question is the net work equal to the negative of the net heat? So let's go look at that. So now the net heat, again, look at this thing. I gotta add these guys right there. So then this means here is that this is going to be positive 606 plus 0 minus 412, and I get a value of positive 94 joules. Okay, now let's do the network here. Again, if you look at the network, I'm just adding these guys in this column here. And then you see here that this is going to be 0 minus 356 plus 165, and I get a value of negative 191 joules. Again, I would say that the reason why these guys are not the same is due to rounding errors. So when I look at my values, I get positive 194 joules, and here I get negative 191 joules. I'm saying that that matches up perfectly.